Hello everyone and welcome to the Frontiers of Parameterized Complexity. Our speaker today is Karthik Chandrasekaran, who will speak on hypergraph k-cut for fixed k in deterministic polynomial time. Please, Karthik.
Thank you. Thank you for inviting me. This is based on joint work with Chandrasekaran. Please feel free to stop me if you have any questions or write your questions in chat, or if you want to unmute yourself and ask the question, that's fine too. Please feel free to stop me. Okay. Let me begin by introducing hypergraphs. A hypergraph is specified by a vertex set and a collection of hyperedges. A hyperedge is a subset of vertices. If every hyperedge has at most two vertices, then the hypergraph is simply a graph. So hypergraphs generalize graphs. In this work, we are interested in hypergraph cuts and hypergraph k-cuts. A subset of hyperedges is said to be a cut set if its removal leads to at least two connected components. In this example, the removal of the red hyperedge does not lead to two connected components, so the red hyperedge does not form a cut set. But the removal of, let's say, the red and black hyperedges leads to two connected components, so the red and black hyperedges together form a cut set. More generally, a subset of hyperedges is said to be a k-cut set if its removal leads to at least k connected components. In this example, the removal of the red and orange hyperedges leads to three connected components, so the red and orange hyperedges together form a three-cut set. Note that they also form a two-cut set. Equivalently, a subset of hyperedges is said to be a k-cut set if it crosses some k partitioning of the vertex set. A k partitioning of the vertex set is a partition of the vertex set into k non-empty parts, and a hyperedge is said to cross the partition if it intersects at least two different parts of the partition. In this example, here is a three partition of the vertex set. The red and orange hyperedges cross this three partition, so the red and orange hyperedges together form a three-cut set. In the hypergraph k-cut problem, we are given a hypergraph and a fixed constant k. Think of k as 2, 3, 4, 5, 10, 100, and so on. It is a fixed constant that is independent of the size of the hypergraph. That is independent of the number of vertices in the hypergraph. And we would like to find a minimum cardinality subset of hyperedges whose removal leads to at least k connected components. One can also consider the weighted version of the problem, where we have non-negative weights on the hyperedges, and we would like to find a minimum weight k-cut set. I am focusing on the cardinality version for the sake of simplicity. Everything that I say in this talk holds for the weighted version as well. Right. The special case of this problem, where the input hypergraph is in fact a graph, is known as the graph k-cut problem. There is a fundamental structural difference between the hypergraph k-cut problem and the graph k-cut problem. For graph k-cut in connected graphs, the removal of a minimum cardinality k-cut set will lead to exactly k connected components. Whereas for connected hypergraphs, the removal of a minimum cardinality k-cut set may lead to more than k connected components. For example, look at this example. The purple hyperedge here forms a minimum cardinality two-cut set. but its removal leads to more than two connected components. So in this sense, hypergraph K-cut problem differs from graph K-cut problem. The hypergraph K-cut problem can equivalently be phrased as a partitioning problem. Here is the equivalent way of phrasing it. We would like to find a K partition of the vertex set with minimum number of crossing hyperedges. Recall that a K partition of the vertex set is a partition of the vertex set into K non-empty parts, and a hyperedge is said to cross the partition if it intersects at least two different parts of the partition. And we take the partitioning viewpoint in this work as it is helpful while designing algorithms. And in fact, hypergraph partitioning problems were introduced as early as 1976 by Lawler. There are several interesting objectives while considering hypergraph partitioning. In this work, we consider the K-cut objective, which is to minimize the number of crossing hyperedges. Okay, any questions up to this point? Any questions on the problem definition?
Hello?
Yes.
Yeah, can you just go back to the example you just gave to explain? Yeah, can you just repeat what you mentioned?
Right, so the removal of a minimum cardinality K-cut set may lead to more than K connected components in hypergraphs. And this is not the case in graphs. For example, here, the minimum cardinality two-cut set should have size 1. And in fact, if you remove the purple hyperedge, you see that we do get at least two connected components. But in fact, we get more than two connected components. We get three connected components.
Okay, thank you.
So the removal of a minimum cardinality K-cut set in hypergraphs may lead to more than K connected components. And this is not the case in graphs. And this is a structural difference, which also makes designing algorithms more difficult. Okay, why do we care about this problem? There are both practical as well as theoretical motivations to study this problem. On the practical side, it has applications to network connectivity, reliability, clustering, etc. The partitioning viewpoint has applications in clustering. And moreover, the special case of graph K-cut is important for solving the traveling salesman problem. Graph K-cut is used to generate cutting planes while solving the traveling salesman problem. On the theoretical side, note that the hypergraph K-cut problem generalizes the global min-cut problem in graphs and hypergraphs. In particular, hypergraph 2-cut problem is simply the global min-cut problem in hypergraphs. So it is natural to ask if we can solve this more general problem. Okay, if we can solve hypergraph 2-cut, then can we solve hypergraph 3-cut? Can we solve hypergraph 4-cut and 5-cut and so on? The second important theoretical motivation to study the hypergraph K-cut problem comes from its connection to the more general submodular K partition problem. In the submodular K partition problem, we are given a submodular function over a ground set V via an evaluation oracle and a fixed constant K. We would like to find a K partition of the ground set to minimize the sum of the function values of the parts. Submodular K partition was introduced by Zav, Nagamuchi, and Ibaraki. It generalizes partitioning problems over several interesting discrete structures. And we still do not know the complexity of submodular K partition. Maybe it is NP hard, maybe it is solvable in polynomial time. We still don't know this. And it turns out that hypergraph K-cut is a special case of submodular K-partition. This was shown by Okamoto, Fukunaga, and Nagamuchi. I would like to take a couple of minutes showing this reduction. Why is hypergraph K-cut a special case of submodular K-partition? Most of you may be familiar with the fact that the hypergraph cut function is submodular. So it is tempting to use the hypergraph cut function as the submodular function in the reduction. And maybe wonder, maybe the reduction is immediate. But if you use the hypergraph cut function as the submodular function, then the submodular K-partition objective tends to overcount the number of crossing hyperedges. So just to illustrate this, let's look at the same example again. Look at this 3 partition. The number of hyperedges crossing this 3 partition is 2. Only the red and orange hyperedges cross this 3 partition. But the submodular K-partition objective, submodular 3 partition objective is the sum of the function values of the 3 parts. If you take the submodular function to be the hypergraph cut function, then the sum of the function values of the 3 parts becomes 6. This is overcounting the number of crossing hyperedges. So we cannot simply use the cut function of the hypergraph as the submodular function. We have to be a little more careful in this reduction. Here is the reduction. For each hyperedge, let us fix a head vertex in the hyperedge arbitrarily. Look at the red hyperedge, fix a head vertex in the red hyperedge arbitrarily. Look at the purple hyperedge, fix a head vertex for the purple hyperedge, and so on. For each hyperedge, fix a head vertex in the hyperedge arbitrarily. Now define a function over subsets of vertices. The function value of a subset S is the number of hyperedges crossing S and having their heads in S. This function turns out to be submodular. This is nothing but orienting the hyperedges and defining f to be the cut function of the directed hypergraph. So f turns out to be submodular. And in fact, the submodular K-partition objective for this choice of the submodular function f correctly counts the number of crossing hyperedges. And just to see this, look at this 3 partition, V1, V2, V3 again. The number of hyperedges crossing this 3 partition is 2. And the sum of the function values of the 3 parts is also 2. The function value of V1 is 1 because the hyperedges that cross V1 and having their heads in V1, there is only one such hyperedge, namely the orange hyperedge. So f of V1 is 1. Function value of V2 is also 1. There is only one hyperedge contributing to f of V2, namely the red hyperedge. And the function value of V3 is 0 because none of the hyperedges have their heads in V3. So with this choice of the submodular function f, the submodular K-partition objective correctly counts the number of crossing hyperedges. So hypergraph K-cut is in fact a special case of submodular K-partition. And as I mentioned before, we do not yet understand the complexity of submodular K-partition. And we will see that we have a very good understanding of a special case, namely graph K-cut. So in this sense, hypergraph K-cut acts as a nice bridge between the very well understood graph K-cut problem and the not so well understood submodular K-partition problem. And the hope is that studying hypergraph K-cut will help us eventually understand submodular K-partition. Okay, any questions so far? Okay, next let me briefly highlight the challenges involved in solving such graph partitioning problems. For this, let me go back to graph K-cut. How do we solve graph K-cut? Well, let's first talk about graph 2-cut. how do we solve graph 2 cut? How do we solve global min cut in graphs? Well, the first approach is to solve min-ST cut for all possible pairs S and T and return the cheapest. One could try to extend this approach for larger constants K. For each set of K distinct terminal nodes, solve this subproblem, namely find a minimum number of edges to remove so that the K terminal nodes are separated from each other and return the cheapest. Now, this approach would be viable if we can solve this subproblem. But this subproblem is the multi-way cut problem, which is NP hard even for K equals 3. So the first approach, which works for graph 2 cut, already fails for graph 3 cut. Graph 3 cut is already non-trivial, yet it is solvable in polynomial time. This was first shown by Goldschmidt and Hochbaum. They gave a deterministic n to the k squared time algorithm to solve graph k cut, where n is the number of vertices in the input graph. Recall that k is a fixed constant, so running times of this form would be considered as polynomial time. After this, Karger and Stein gave a randomized contraction-based algorithm that runs in time n raised to 2 times k minus 1 times polylog n. As you can see, there is a difference between the deterministic and randomized runtime. In a series of works, the deterministic runtime was improved to almost match the randomized runtime. This was the status for a long time. The last couple of years has seen a lot of exciting works on graph k cut. Very interesting techniques have been proposed. And one of the cool results here is showing that the Karger-Stein's randomized algorithm, in fact, runs in time n to the k. Right, this is the status for graph k cut. There are also FPT algorithms. I'm not going into the FPT literature since we're not going into FPT for hypergraph k cut. This was the status for graph k cut. And ever since the first result of Goldschmidt and Hochbaum showing that graph k cut is solvable in polynomial time, the complexity of hypergraph k cut has been open. And we're not the first ones to talk about this. There has been some partial progress in the literature towards hypergraph k cut. Let me run through the partial progress to build some familiarity with this problem. The first interesting case of hypergraph k cut that you would like to solve is when k equals 2. This is the global min cut problem in hypergraphs. How can one solve global min cut in hypergraphs? Well, global min cut can be solved in hypergraphs if we can solve min-ST cut in hypergraphs. And here is one approach to solve min-ST cut in hypergraphs. Consider the bipartite representation of the hypergraph. In the bipartite representation, we have nodes corresponding to vertices of the hypergraph on the left side, and nodes corresponding to hyperedges of the hypergraph on the right side. And each hyperedge node is adjacent to all vertices that it contains. This is the bipartite representation of the hypergraph. Now, in order to solve min-ST cut in the given hypergraph, it suffices to solve a node capacitated max ST flow in the bipartite representation, which can be done in polynomial time. In fact, it can be done in deterministic polynomial time. So min-ST cut in hypergraphs can be solved in deterministic polynomial time. Do keep this in mind. We will come back and use this later. And this implies a folklore way to solve global min cut in hypergraphs. Beyond going via min-ST cut, there are also faster ordering-based algorithms and random contraction-based algorithms to solve global min cut in hypergraphs. So we can solve hypergraph 2 cut. The next interesting case is hypergraph 3 cut. In 2008, Xiao gave a deterministic algorithm to solve hypergraph 3 cut. So what is open is the complexity of hypergraph k cut for k at least 4. The next interesting restriction that has been studied in the literature is on the input family of hypergraphs itself. The rank of a hypergraph is defined to be the size of the largest hyperedge. If the rank of the input hypergraph is 2, then the hypergraph is simply a graph, and we know how to solve graph k cut. If the rank of the hypergraph is a constant, then the hypergraph should intuitively behave like a graph. So intuitively, the techniques for graph k cut should port over for hypergraph k cut in constant rank hypergraphs. This is the intuition. This was formalized by Fukunaga. He gave a deterministic algorithm, polynomial time algorithm, to solve hypergraph k cut in constant rank hypergraphs. That is when the size of all hyperedges in the input hypergraph are a constant. So what is open is the complexity of hypergraph k cut for k at least 4 in arbitrary rank hypergraphs. That is when the input hypergraph could have large hyperedges. As many hyperedges as the number of vertices, or maybe n over 2 or n over 4. Size of hyperedges as big as n over 2 or n over 4 and so on. Right, so this was the status for a long time. A couple of years ago, we took a solid step towards answering this question. We gave a randomized polynomial time algorithm to solve hypergraph k cut in arbitrary rank hypergraphs. And our work was followed up by Fox, Panigrahi, and Zhang, who gave a faster randomized polynomial time algorithm. Nevertheless, both our algorithms are based on random contraction approach, which does not extend to submodular k partition. And moreover, both are randomized algorithms. When we talk about the complexity of an optimization problem, we want to bring it into the complexity class P, so we would like deterministic polynomial time algorithms. So that brings us to the main result of this work. We give a deterministic polynomial time algorithm to solve hypergraph k cut in arbitrary rank hypergraphs for every constant k. Any questions on previous work and the result? Okay, let me tell you a bit about the techniques. The main technique underlying our deterministic algorithm is to use min-ST cuts to recover the parts of an optimum k partition. Min-ST cut for arbitrary choice of S and T will not recover the parts of an optimum k partition. We show that min-ST cuts for certain choices of S and T will recover the parts of an optimum k partition. To tell you more about our technique for hypergraph k cut, let me take a step back and recall the technique for graph k cut introduced by Goldschmidt and Hochbaum. Again, what is the graph k cut problem? We are given a graph and a fixed constant k. We would like to find a k partition of the vertex set with minimum number of crossing edges. The approach taken by Goldschmidt and Hochbaum is to try and recover a part of an optimum k partition. If you can recover one part of the optimum k partition efficiently, then you can remove this part, remove this subset of vertices from the graph, and recurse on the remaining graph to find an optimum k minus 1 partition. Right? This is the approach. To elaborate on this approach, I will make two simplifying assumptions on the input graph. Firstly, I will assume that all cut values in the input graph are distinct. This in particular means that min ST cut is unique for every choice of S and T. And secondly, I will assume that there exists a unique optimum K partition, which I will denote as V1 through Vk. Now, these two assumptions, well, you can relax them with careful tie-breaking rules. I'm not going to bore you with the tie-breaking rules. Instead, I'm going to work under these assumptions. All cut values are distinct, which implies that min ST cut is unique for every choice of S and T. And there is a unique optimum K partition, which I will denote as V1 through Vk. And you can also make these assumptions in the weighted case when you have weights on the edges. You can perturb the weights slightly, maybe randomly, without changing the optimum, so you will achieve these two assumptions. So that's one way to justify the assumption, but in our work, we also relax these assumptions with careful tie-breaking rules. So I'm not going to bore you with the tie-breaking rules. We will work under these two assumptions. Okay, now in order to recover a part of an optimum K partition, to go through this approach, Goldschmidt and Hochbaum showed a nice structural result. Here is their structural result for graph K cut. Look at the optimum K partition. We said the optimum K partition is unique, V1 through Vk. Let's consider this optimum K partition. Without laws of generality, let V1 be the part with cheapest cut value. Now, Goldschmidt and Hochbaum showed that for every choice of T that is disjoint from V1 and intersecting each of V2 through Vk, there is a subset S inside V1 of small size, of size at most K minus 2, such that the minimum ST cut is exactly V1, V1 bar. Recall that all cut values are distinct. So minimum ST cut will be unique for every choice of S and T. And this is saying the minimum ST cut is exactly V1, V1 bar. For me, a cut is an ordered pair. There is the source side and the sink side. The first set in the ordered pair is the source side. Again, the structural theorem says that for every T that is disjoint from V1 and intersecting each of V2 through Vk, there is a subset S inside V1 of small size, of size at most K minus 2, such that the minimum ST cut is exactly V1, V1 bar. Now let's see how to use this structural theorem to design an algorithm for graph K cut. The structural theorem allows us to enumerate a polynomial-sized family of subsets containing V1. Here is how we would enumerate this. We initialize the family to be empty. For each subset S of at most K minus 2 vertices and each subset T of K minus 1 vertices, we compute the minimum ST cut, U bar, add the source side U to the family F. Now, by the structural theorem, this family F contains V1. Why does this family F contain V1? Well, consider applying the structural theorem to the set T that has exactly one vertex from each of V2 through Vk. The size of such a set T is K minus 1. And the structural theorem tells us that there is a subset S of size at most K minus 2, such that the minimum ST cut is exactly V1, V1 bar. Now, such a pair ST is considered by this procedure, so V1 will be in the family F. Now, what is the size of the family F? Well, the size of the family is n to the order K. And the time to compute the family is n to the order K min ST cut computations. Recall that min ST cuts in graphs can be solved in polynomial time, so the runtime is n to the order K. Now we have a polynomial-sized family of subsets containing V1. With this observation, here is the algorithm. Use this procedure to find the family F. For each subset U in the family, we recurse by removing U and looking at the remaining graph to find a min k minus 1 partition. Recurse on G minus U to find a min k minus 1 partition, say P1 through Pk minus 1. Now compute the cost of the K partition, U comma P1 through Pk minus 1 in G. And return the cheapest K partition among all that we have computed. The correctness of this three-step algorithm follows from the fact that the family F contains V1 and by induction on K. So let's talk about the runtime of the algorithm. The runtime of the algorithm to solve min K partition on an n-vertex graph T of mk is the time to compute the family F, which is n to the order k, plus the size of the family times the runtime of the algorithm to solve min k minus 1 partition on an at most n-vertex graph. Now substitute the size of the family n to the order k and solve this recursion. You see that the runtime is n to the order k squared.
I have a question.
Yes.
So in the algorithm, why is it enough to consider only t of size k minus 1?
Oh, yeah. So why is it enough to consider subset T of size k minus 1? Let's apply this. So yeah, let's argue why is this statement true. Let's fix this algorithm. Why is this statement true? Consider applying the structural theorem to a set T. Note that the structural theorem holds for every set T that is disjoint from V1 and intersecting each of V2 through Vk. So apply the structural theorem to a set T which contains exactly one vertex from each of V2 through Vk. And for such a subset T, the structural theorem tells us that there is a subset S of small size, of size at most k minus 2, such that the minimum ST cut is V1 bar. Now, what is the size of T? The size of T is exactly k minus 1, because it has exactly one vertex from each of V2 through K.
Okay, thank you.
Mm-hmm. Right. Any other questions on this approach by Goldschmidt and Hochbaum for graph K-cut?
So you also mentioned that there are special conditions, right, on the uniqueness of the K-cut. So
right. I assume those two simplifying assumptions, that the minimum ST cut is unique for every choice of S and T, and the optimum V1 through Vk is also unique.
So the structural theorem, it holds only under these conditions, or they use them for something else?
Well, yeah, you'll have to throw in some tie-breaking rules. So you'll have to pick a specific choice of the optimum, V1 through Vk, and you cannot take an arbitrary min ST cut. You will have to take a source maximal min ST cut.
Oh, thank you.
Yeah, yeah, I didn't want to throw in those extra tie-breaking rules. So yeah, but it still holds. So you can break ties, and there is a version of the structural theorem without those assumptions. Okay, so this is the approach by Goldschmidt and Hochbaum for graph K-cut. Now let me tell you about our approach for hypergraph K-cut. Our approach closely resembles the approach of Goldschmidt and Hochbaum. We also try to recover a part of an optimum K partition. And to elaborate on this approach, I will again work under these two simplifying assumptions on the input hypergraph. Namely, all cut values are distinct. So min ST cut is unique for every choice of S and T. And there exists a unique optimum K partition, which I will denote as V1 through Vk. Okay, now in order to recover a part of an optimum K partition, we also show a clean structural result. Our structural result closely resembles the structural result of Goldschmidt and Hochbaum. So let me first state our structural result, and then I will contrast it with the structural result of Goldschmidt and Hochbaum. Okay, here is our structural result. Again, look at the optimum K partition, V1 through Vk. We assume that it is unique, focus on it. Now let's focus on an arbitrary part of the optimum K partition. Let's focus on V1. V1 be an arbitrary part. Now we show that for every subset T that is disjoint from V1 and intersecting each of V2 through Vk, there is a subset S inside V1 of small size, of size at most 2k minus 2, such that the minimum ST cut is V1, V1 bar. Again, we assume that all cut values are distinct, so minimum ST cut is unique. And this structural theorem is saying for every subset T that is disjoint from V1 and intersecting each of V2 through Vk, there is a small size subset S such that the minimum ST cut is V1, V1 bar. We show this for hypergraphs, first of all, and this structural theorem, this version of the structural theorem was not known even for graphs. Let me contrast the structural theorem with the structural theorem by Goldschmidt and Hochbaum for graphs. This is the structural theorem by Goldschmidt and Hochbaum for graphs. There is one crucial difference between the two structural theorems. One, it's in the assumption. For Goldschmidt and Hochbaum structural theorem to hold, they crucially rely on V1 being the cheapest part. It is the part with the cheapest cut value. Whereas our structural theorem holds for any part of the optimum K partition. There is nothing special about V1, so it holds for every part of the optimum K partition. So in this sense, our structural theorem is stronger even for graphs. But on the other hand, since our structural theorem is trying to find an arbitrary part of the optimum K partition, the bound on the size of S that we get is weaker than the bound on the size of S given by Goldschmidt and Hochbaum. We get a bound of 2k minus 2, they get a bound of k minus 2. And in fact, this 2k minus 2 in our structural theorem is tight even for graphs. There is no hope, there is no room to improve this 2k minus 2. The structural theorem does not hold if you replace 2k minus 2 by even 2k minus 3, even for graphs. So this is tight. And one more remark, the proof of the structural theorem of Goldschmidt and Hochbaum that they give is heavily based on the properties of the graph cut function. It is a bit hard to follow. They count graph edges very carefully throughout their proof, and it's a bit hard to follow. Whereas we break the proof of our structural theorem into two clean parts. The first part depends only on submodularity, and the second part still relies on properties of the hypergraph cut function, which, we still have to do some careful hyperedge counting, but we have managed to split the proof into two parts. First part relies only on the submodularity of the hypergraph cut function. So in a sense, the first part holds even for general submodular functions. And if you're interested in understanding what is going on in Goldschmidt and Hochbaum's proof, I suggest seeing our proof. We have split it, so the writing style might help you understand, to interpret what is going on in their proof. And I have to say one final remark. Ferran in '98 claimed that Goldschmidt and Hochbaum structural theorem also extends to symmetric submodular K partition, but he subsequently retracted this claim. He couldn't prove it, I guess. But using our modularized proof technique of the structural theorem, we can in fact show that Goldschmidt and Hochbaum structural theorem indeed holds for symmetric submodular K partition. We discuss some more about this implication in our upcoming SODA work. Okay. Any questions on the structural theorem and its difference to the structural theorem of Goldschmidt and Hochbaum for graphs? Okay, let's see how to use the structural theorem to design the deterministic polynomial time algorithm for hypergraph K-cut. The structural theorem allows us to enumerate a polynomial-sized family containing all parts of the optimum K partition. Here is how we would do this. Initialize the family F to be empty. For each subset S of at most 2K minus 2 vertices and each subset T of K minus 1 vertices, we compute the minimum ST cut at the source side to the family. By the structural theorem, the family F contains V1, but the structural theorem holds for any part of the optimum K partition. So it also implies that the family F contains all parts, any part of the optimum K partition. So it contains V2 through Vk as well. Now, what is the size of the family? Well, it is still n to the order K. And the time to compute the family is n to the order K min ST cut computations. Recall that min ST cut in hypergraphs can be solved in deterministic polynomial time. So we now have a family F, a polynomial-sized family F, containing all parts of the optimum K partition. So you don't have to recurse like Goldschmidt and Hochbaum. Here is the simple algorithm. Use this procedure to find the family F and consider all possible K subsets of the family F that form a K partition and return the cheapest. The correctness of the algorithm follows from the fact that the family F contains all parts of the optimum K partition. Let's talk about the runtime. The runtime is the time to compute the family, which is n to the order K min ST cut computations, plus the size of the family choose K. The size of the family is n to the order K, so the runtime is n to the order K squared. And note that this is a deterministic polynomial time algorithm because min ST cut computations can be done in deterministic polynomial time. Okay, in the remaining time, remaining 10 minutes or so, I would like to show you an outline of the proof of the structural theorem. But before I do that, let me interpret the structural theorem for K equals 2. What does the structural theorem say for the special case of hypergraph 2 cut? That is, what does it say for global min cut in hypergraphs? So let's interpret the structural theorem. Still keep in mind that all cut values are distinct. So min ST cut is unique, which in particular means that global min cut will be unique. Okay, so let's interpret the structural theorem for global min cut. It says that for every subset T that is disjoint from V1, that is T is completely contained in V2 and it is non-empty, there is a subset S inside V1 of size at most 2K minus 2 where K is 2. So there is a subset S inside V1 of size at most 2 such that the minimum ST cut is exactly V1, V2. Now, if you think about the statement, this is in fact obvious for global min cut. In fact, you can say a slightly stronger statement for global min cut. For every subset T of V2 that is non-empty, and for every subset S of V1 that is non-empty, the minimum ST cut has to be V1, V2, because V1, V2 is the global min cut. So something stronger holds for global min cut. So in some sense, our structural theorem is a generalization of what happens for global min cut. Okay, let me briefly sketch the proof outline. I won't get very technical, but I'll get somewhat technical. Okay, let me redraw the optimum K partition V1 through Vk. We would like to show the structural theorem for every subset T of this form. So let us fix a subset T as in the theorem. That is a subset T that is disjoint from V1 and intersecting each of V2 through Vk. Now look at any subset S inside V1, not necessarily a small size subset. Look at any subset S inside V1. Now look at min ST cut. Min ST cut has source side and sink side. It will separate S and T. I will denote the source side by V subscript S. Min ST cut separates S and T, so it's going to be of this form. Now we prove the structural theorem in two steps. First step, we show a containment that for every subset S that is contained in V1, the source side of the min ST cut will be completely contained in V1. That is, all these boxes are in fact empty. The source side of the min ST cut is fully contained in V1. This containment takes you halfway to the structural theorem. In particular, if you take S to be equal to V1, then what is the minimum V1 to T cut? Well, it has to be contained in V1 and it fully contains V1. So the minimum V1 to T cut is exactly V1. And in particular, if the size of V1 itself is small, if the size of V1 is at most 2k minus 2, then you can simply take S to be equal to V1 and you will get the conclusion that you want for the structural theorem. So the containment lemma takes us halfway to proving the structural theorem. So the interesting case is when the size of V1 is more than 2k minus 2, it's large. Maybe it's n over 2 or something very large. Next, we show a small witness lemma that there exists a subset S inside V1 of size 2k minus 2, such that the source side of the minimum ST cut is exactly V1. Right, this small witness lemma uses the containment lemma. The proof of the small witness lemma relies on the containment lemma and an uncrossing argument. These are the two steps to our proof. The containment lemma is an uncrossing argument. The proof is based on an uncrossing argument, which relies only on the submodularity of the hypergraph cut function. In fact, containment lemma, in some sense, also holds for any submodular function. But the small witness lemma is where we need to rely on the hypergraph cut function properties. The proof of the small witness lemma is also based on an uncrossing argument, but the uncrossing argument has to use more careful hyperedge counting. And we currently do not have a very simple proof of the small witness lemma. It seems like we do have to do hyperedge counting here. Right, these are the two steps to our proof. In the interest of time, I won't go into the details of the proof of these two lemmas, but they're not very hard. In fact, they're very clean and they come out very nicely. I encourage you to read the paper. Let me wrap up. We already saw how to use the structural theorem to design a deterministic polynomial time algorithm for hypergraph K-cut. Our main contribution is the structural theorem showing that min ST cuts can be used to recover the parts of an optimum K partition. And we use the structural theorem to get a deterministic polynomial time algorithm for hypergraph K-cut. The runtime of our algorithm with tie-breaking rules is n to the order k squared min ST cut computations. We also give a better structural theorem which leads to a faster algorithm. The runtime of the resulting algorithm is n to the 8k min ST cut computations. Okay, let me wrap up with some open questions. We gave a deterministic polynomial time algorithm for hypergraph K-cut. The current best runtime is n to the 8k min ST cut computations. Can we improve this deterministic runtime? Can we bring down the dependence on K? Can we solve hypergraph K-cut maybe in n to the 4k or n to the 2k or n to the k min ST cut computations? Also, it would be interesting to improve the randomized runtime. The randomized runtime, I believe, is n to the 2k for hypergraph K-cut, but with the latest result for graph K-cut, the randomized runtime is n to the k. So can we improve the randomized runtime for hypergraph K-cut? Another nice open question here is whether we can enumerate all min K-cuts in hypergraphs in deterministic polynomial time. Recall that we can enumerate all min K-cuts in graphs in polynomial time. The number of min K-cuts in graphs is polynomial. You can show this using the Karga's random contraction technique. So you can enumerate all min K-cuts in graphs in randomized polynomial time using Karga's random contraction technique. You can also enumerate all min K-cuts in graphs in deterministic polynomial time. And there is a counterpart of the polynomial bound for hypergraphs. The number of min K-cuts in hypergraphs is polynomial. This comes out of the random contraction based algorithm for hypergraph K-cut. But we do not know how to enumerate all min K-cuts in hypergraphs in deterministic polynomial time. We can do this currently in randomized polynomial time. Question is, can we do this in deterministic polynomial time? And the reason I'm posing this is because I believe that, again, an algorithm for this has to rely on some nice structural result. It would be interesting to understand what structural result enables this algorithm to enumerate. And going back to the main motivation of all of this, can we resolve the complexity of submodular K partition? Is it NP hard or poly-time for fixed constants K? All right, I'll stop here. Thank you very much for your attention.
Thank you very much, Karthik. That was for a nice talk. So, any questions?
Hi, I have a question. First of all, thanks for a very nice talk. You said in the beginning that this hypergraph version acted as a stepping stone between the graph problem and the submodular problem. Now that the hypergraph one is solved, is there any obvious next stepping stone on the way to the full generality of submodular functions?
Right, so the natural approach here is to try and prove the structural theorem for submodular functions. So let me flash the structural theorem. So min ST cut is again well defined for submodular functions. You're familiar with that. So it's one natural approach is to try and prove this structural theorem, not only for hypergraphs, maybe even for submodular functions. But yeah, we do have counterexamples to the structural theorem for submodular functions. So yeah, in this form, the structural theorem does not hold. One could ask, what if I relax this bound? Maybe size of S at most K squared, or maybe something larger. We still, yeah, we believe we have counterexamples for all of that. So this approach does not seem to extend to submodular functions. Yeah, one of the reasons why we wanted to explore this approach was to prove that it would work for submodular K partition, but we failed miserably on that front. But as we were doing some experiments, we realized that it seems to hold for hypergraphs with this kind of bound, 2k-2 bound, and that's how we set about trying to prove the structural theorem. So that's how we even, yeah, but that's why we had to settle for this problem.
I see, thanks.
So if there are any other questions, then thank you very much once again. And I see all of you within 2 weeks. Goodbye.
Thank you.